Okay, so now we get to the other way that we're going to combine all these various different gas laws, and this is going to be into something that we're going to call the ideal gas law. And the ideal gas law is actually the most important and most used gas law on the AP exam. So the reason that the ideal gas law is different from the combined is that it adds one more variable. So earlier in the year, we had talked about Avogadro's law and this whole any 1 mole of gas occupying 22.4 liters at STP. So, we use that in stoichiometry. 1 mole equals 22.4 liters at STP. It was a useful thing. But if that's the case, then that means the amount of a gas is tied to both the volume, the pressure, right? The volume, the pressure, and the temperature of that gas. And that's exactly what we've been doing. So that means we're going to have a new variable that we can add, and that new variable is going to be a lowercase n, and that lowercase n is going to stand for moles. Don't ask me why N stands for moles, but the lowercase m would be mass, so we can't have it stand for moles. And I think this lowercase n really stands for number of moles, is I think where that's coming from, and that's why n is moles. But regardless, what it is we have this formula, PV equals nRT. And you will also often hear people call this as perv nert, that's the ideal gas law. Perv nert, I use it all the time. But it's a much easier formula to deal with because there are no denominators, everything is multiplied. So that way, if we want to solve for pressure, it's simply nRT over V. If you want to solve for volume, it's simply nRT over P. If you want to solve for moles, that N, it's PV over RT. And if you want to solve for T, it would be PV over NR. So P is pressure, V is volume, N is moles, T is temperature, and temperature again, still always in Kelvin. But what is R? And R is what we refer to as the gas law constant. It is a constant. It's the thing that makes all of these other 4 variables work. So the ideal gas law and this gas law constant are both on the formula sheet, which is lovely. Now the thing is, there's multiple different numbers that can be used for R, and they all depend on the pressure variable. So pick the correct R to match pressure units. So I've given you the 2 most common. The one you're going to actually use the most is probably the 0.08206, because that is primarily going to be atmospheres, which is what is most common on the exam. You will use 8.314 during other portions of the course, so you just need to make sure you use the right one. Okay, so why ideal? Like, why did we throw that name in here? Well, it's ideal because there are assumptions that go in there. And the 2 assumptions are that gas molecules have no volume and that gas molecules have no attractive forces between them. Neither of these things are true. Gas molecules do have volume, but not very much in comparison to how much space they take. And gas molecules do have attractive forces between them, but not very strong because they're moving so fast. So we can basically create ideal conditions as long as you keep those 2 things in mind. So you basically want to do everything you can to keep gas molecules from sticking together. So you need to have them occupy large volumes. You want very low pressures. And then you want very high temperatures. So low pressures create large volumes, and high temperatures keep molecules fast, so they can't stick together. So as long as you have those conditions, you're pretty much going to calculate and find out that you are going to achieve ideal conditions. So let's do a quick practice problem. Okay, a 1.45 liter container, that's a volume, is filled with sulfur dioxide gas at a pressure of 115.0 kPa, that's a pressure, and a temperature of 28 degrees Celsius, that's a temperature. How many moles of sulfur dioxide gas are in the container? So that's your N. You will notice I only have one volume and one pressure and one temperature, that there is no change in conditions. That's different than all of the other problems we've done so far. So we've got a P, we have a V, we have a T. R is a constant, we're being asked for N. So that formula was PV over RT. And just like every other time, we have to adjust our T. So 28 degrees Celsius plus 273. That's going to give us 301 Kelvin. So we can plug these values in. So again, just like the other things, I'm going to tell you how to do it in your calculator at the same time. So open a parentheses, pressure of 115.0 kPa times a volume of 1.45 liters, close parentheses, divided by, open a parentheses, R. You have to pick the right R. This R value needs to have the kPa, and to do that, it's the 8.314 value times the temperature of 301 K, close parentheses. So if you do that, and we're going to look, and for pretty much this right here gives me 1, 2, 3 significant figures. So when I do that in my calculator, 0.0667 moles is my answer. So that's how many moles we've got. And then it asks calculate the mass in the container. So sulfur dioxide. Sulfur is going to be S. Dioxide means O2. So this is a straight moles to mass problem. It's one step, but I need the molar mass. Okay. So it's been a while since we've done that, but that should be easy. So sulfur 32.06 plus 2 times 16.00 is going to give me 64.06 grams per mole is my molar mass. So I'm going to start with my moles that I just now calculated of SO2, and I started off with moles, so I need moles in my denominator and grams in my numerator. The molar mass number always goes with the grams. 1 always goes with the moles. So this is a multiplication. My moles of SO2 cancels out, leaving me in grams, which is what the question was asking for. I will still have 1, 2, 3 significant figures. And so it's 0.0667 times 64.06 to 3 significant figures, 4.27 grams of SO2. So it is because you can deal with grams and moles that makes the ideal gas law actually much more important than the combined gas law, and it is by far the one you are going to need to use the most. So remember PervNert. We'll play around with that formula sum in the part 2 video.